PV systems. All right.
Yes.
So let's go, sir. They will meet us here. So we'll be talking,
Okay.
this course content, we'll be looking at fundamentals of solar photovoltaic technology. We'll be looking at overview of a PV system. We'll be looking at how to design a PV system. We'll look at how to install a PV system. We'll look at automatic changeover circuitry, and we'll be looking at panel designing and building. And so I will just quickly do some introductions to all of them. What is fundamentals? We just want to look at everything about the technology around what is a solar PV systems. Overview of a PV system, we'll be looking at what are the components involved in the PV systems. Number 3, we'll be looking at how can you design a PV system for anybody along your area that you know. And we'll be looking at how to install a solar PV system, automatic changeover circuit, how can you design one, how can you build one. That's what we'll be doing. Everything here will be done practically, everything working practically.
Okay.
So panel design, how can I design and build a panel? So our class this morning will be generally want to come to a knowledge of how does solar PV system work, how does this energy is being generated, what are the nitty-gritty along generations of energy. That is what I really want to, because it's like the theoretical basis of everything we are going to be doing. In our company, we don't just train people, just okay, connect this thing, you will get this. You should be able to know what really happens behind the scene, and how did you actually connect them, and how you size them together. So under this particular course called Fundamentals of the PV Systems, we'll be looking at the basic principle of photovoltaic effect, characteristics of the solar PV system, solar terminologies, applications of solar PV systems. Then why is solar trending? Why is it that everybody is using solar these days? So we'll be talking about it.
Because NEPA is calm now.
What is it? NEPA is calm. Wow, sorry. Okay, NEPA is calm, so solar is the solution. Now I understand. All right. You are welcome, sir. All right, sir. So, we'll be starting with the suns and the radiant energy. The sun is a very common thing. Everybody knows that 100% of the energy that the earth uses comes from the sun, directly or indirectly from the sun. So we want to harness energy from the sun. What?
I say that the screen is not showing well. That's some patches. Is it from you or from network? Or?
It's from me, I think so. Is it showing well now?
No. Well, continue. I'll manage. Yeah, it is now.
It's showing well now, Shem? Yeah. All right. So we said
yes.
Directly or indirectly, all the energy we get comes from the sun. All the energy we use on the surface of the earth comes from the sun, directly or indirectly. Plants use photosynthesis to convert the energy from the sun to get food for us. Likewise, animal eats the plant to give us animal proteins also. So almost energy that we get from, even the tides, the ocean current, everything comes from the sun. But that is not my work this morning. My work this morning is to look at how did we harness the energy from the sun and convert it to electricity. And that is what solar PV system is all about. We are harnessing the energy from the sun and we are converting it directly to electricity. I will do some little reasons why we need to convert it to electricity, maybe later in the day in this course. And secondly, I want to tell us that it's not only that energy from the sun can be converted to electricity only. Some people convert energy from the sun to thermal, to heat water, to boil things. So that such system is called solar thermal systems, a thermal system. So, but the one we are looking at in this class will be the one that will generate electricity. You can see a solar panel behind me. So, all right, let's start from the very basics. Now, the very basics is that if you have, when I was growing up, I had some little issue. One of my issues with science is that I always think that we live inside the earth. But as a matter of fact, if you really want to understand today, we live, if there's anybody still in my theory, we live on the surface of the earth. So if this is the earth,
Yes.
this is where we live. Where you actually sit
Yes.
now, where your chair, your table is, on top that thing is called the earth. So now anything that happens to the earth, if the earth is rotating, we are rotating with the earth. Now, the sun is somewhere at a distance to the earth like this. The sun is at a distance like
Yes.
this. Now, the earth rotates in two different rotations. The earth exhibits two different rotations. One along its axis. So that means there is a central axis that is inside the earth that goes into the
Yes.
earth. So the earth rotates along its axis. And the earth rotates along its elliptical orbit. Something of this nature. So that's what really happens. Now, as it rotates along its axis, it completes the rotations together. It rotates along its orbit also together. Now, if Earth rotates one complete revolution along its axis, that gives us a day. That responsible for
Yes.
day. Then, if you rotate complete revolution along its elliptical orbit, that gives us a year. It takes 24 hours for Earth to rotate along its orbit, while it takes 364 1/4 days for Earth to rotate along its elliptic orbit. Now, all such rotations is that the sun is a fixed object, while the Earth rotates around the sun, the planetary orbit. All right, if we have set those very simple bases, now I want to do another experiment for us. This class I will be demonstrating so many things with experiment. Imagine what happens to my hand as it gets closer to the camera. My hand gets bigger and it gets smaller as it gets back away from the camera.
Yes.
That means that if you are actually looking at sun and it's at a farther distance like that, and you are seeing it as that image, the sun is not actually a small object. It's a very massive object. That's what simply means. Now, so the sun is a sphere of intensely hot gas. I'm on the screen now, with about diameter of 1.39 times 10 raised to power 9 meter, and it's about 1.5 times 10 raised to power 10 meter away from the surface of the earth. All right. The solar radiations from the sun passes through the space and through the atmosphere before reaching the surface of the earth. All right. So this is the sun. This is the surface of the earth. So the surface of the earth is covered by something called atmosphere. If you just look at your front like this thing in front of me is called the atmosphere. It's what it's not actually, it's an imaginary thing that covers the earth like this. It's called the atmosphere. Now, after you leave the atmosphere, you enter something called the biosphere. Then you enter something called the troposphere, the ionosphere. Then you leave those spheres and you go to where sun is. Now, what we say is that the energy that the sun is pointing to the earth pass through all those layers before it reaches the surface of the earth. If radiation passed like that, three things can happen to that radiation. It can be filtered, it can be reflected, it can be absorbed. If I have a mirror here, and I point a torch on the mirror, what you will discover is that you will find a reflected image somewhere. That data, sorry, sir. So there is a part of radiation that you point, it's a point of a torch you point also that will reach where you are actually pointing it to. Also, there is some that will be absorbed within the material medium. So these three things happens to the sun radiations as it comes to the earth towards your surface. Now, I really don't want to bore us with so much theory so that we can. Now, irradiance. Irradiance is defined as the total solar radiations per unit time that falls on the surface of the earth, and it's measured in watts per meter square. Please, the reason why I really want us to follow me as I explain all these little concepts. They were not just like I'm teaching us theory. There were things that form the basis for this guy. and you really need to know how this affects this. I don't really put up any theories that you don't need, that might be born now. So the total amount of energy, we know now that the energy from the suns that comes to the surface of the earth, so many things has happened to it, but we are opportune to receive a amount on the surface of the earth. That amount is called irradiance. The amount is called irradiance and is measured in watts per meter square. That's its unit of measurement. It's measured in watts per meter square. Now, that means that if the sun is shining like this, and we are on the surface of the earth like this, if the sun is shining and we are on the surface, so if you measure a meter square on the surface of the earth, the amount of energy received from the sun in watts, because time is involved now, so you expect that in power, it's called watts per meter square. It's called the irradiance. All right, let's move on because of insolations. So if you take the whole irradiations per day, if you take it all per day, you sum them together per day, what you will observe is that that thing is called insolation. If you remember from the basic physics that power is equal to energy divided by time. So by the time we are considering time in these equations, that means what we are going to get is energy. So insolation is the total energy received from the sun on the surface of the earth per day. So for 24 hours, what's the insolations? Now solar constant, please, we are really getting into the nitty-gritty. Now, because if you imagine what really happens to us now, we are both in Nigeria, somebody is in Port Harcourt, somebody is in Abuja, me, I'm in Osun State, in Ife here. We don't expect us to receive the same intensity of radiations. Even on the, so we expect variations in the radiation. Why? The surface of the earth is not flat, it's not spherical. The earth is geoid. The simple example of what a geoid look like is if you buy a tangerine and you peel some part off and you put some part, you left some part open, that shape that you form, that irregular shape, is what a geoid look like. Now, so that means some areas will receive high intensity, some areas will receive low intensity as a result of the shape of the earth. Now, if you take the total sum of where the sun is coming to and you divide it by the area, what you will get is what we call solar constant. That means averagely, this area receives this amount of energy per meter square. Averagely, anytime the sun is shining to the surface of the earth, averagely the earth receives this amount. That's where, so insolations, irradiation is just like, now we are considering geographical variations into the matter. Now, the value is around 1367 watt per meter square or 1353 watt per meter square. Now, due to cloudy days, issues around there are trees blocking your radiations, every that happens along the, so scientists decide to make it 1000 watts per meter square as a constant. Now, this is where I need us to get it right. Please, Mr. Donald, are you with us, huh? I know Mr. Ben is with us. This is where I really need us to get it right, please. It's very important. Now, if they tell you that this solar panel behind me is 100 watts, so if they tell you that this solar panel is 100 watt panel, what it means is that if your insolation is 1000 watts.
Now completely
go. Yes, can you hear me, sir?
I don't go press for it.
So what we are saying is that the basis at which you will know whether a panel is at 100 watts is the basis for scientists for measuring it is that if your solar panel can receive 100 watts, 1000 watts per meter square, that panel should give you its rated capacity. Are we together?
Yeah.
Yes.
So it wasn't the reason why I did all those previous explanations so that we can get where the value is coming from. The value was not just jumping. That means in the morning, when there is no, when the solar constant has not reached 1000, what you actually getting is not the rating capacity of your solar panel. That's just the basis. I will quickly draw a graph here and I will show us on the screen now. So the graph is linear. So if you plot the graph of insolation in watt per meter square against power in watt, what you will observe is a linear graph, something of this nature. That means when your insulation, so if I take this point now, all right, I'm coming. So this is the rated power, and this is 1000. Now, please, I don't know if you can see my screen very well. So
Yes.
for the inversion, so this is 1000. So the rated power they gave to you was the power you will get at 1000 insolation. So what we are saying is that possibly you live in an area that your rating is not, the energy you receive as per sun to that area is not up to 1000. You won't get that power. Now, possibly peradventure you live in an area that is getting more than that, you will get more than that power. That is the basis. If I turn these solar panels back to you now, you will see where they wrote it there, that all these things, all these ratings were done assuming that this is at 1000 watt per meter square. Now, Nigeria is a very good country. We are blessed. I have taken a solarimeter. The instrument for measuring insolation is called solarimeter. I'll take a solarimeter for some times to measure. If you look at the intensity we are having where I am now, this one should be around 800 and something. So sometimes in Nigeria, where I live, I've stayed in Osuka, stayed in Benue, stayed in Osun, sometimes we get around 1600. So that means we can actually do well, more than the basis, more than the baseline. No. So, and I said this is value. This value is the basis for calculating the PV output. The module output is calculated from this basis. And that is what I just explained. I hope I could be able to turn these solar panels back and show you that all these conditions, everything was measured at 1000 watts per meter square. And that's what we try to explain. That now, radiations from the sun can be absorbed, can be reflected, and can be filtered. Now, some areas are actually blessed that they receive something called beam radiations. Beam radiation is that radiation that was not distorted by anything. It just came directly from the sun to the surface of the earth. So that is what really happens in beam radiations. But why we have radiation, diffuse radiation, is the one that has entered the cloud has scattered it before it reached the surface of the earth. Where if I would tell us that Nigeria is not blessed in that area, Nigeria doesn't receive beam radiations, we receive diffuse radiations from the sun.
So isn't beam radiation not dangerous?
Yes, I think it's dangerous also.
All right.
So
Sorry, continue.
yes, so we are still lucky. All right, at least we are lucky because I don't know if you have passed through Nasarawa Axis before. There is this Nasarawa Axis. If you have passed through Nasarawa Axis before, there is this 500 megawatts of solar farm that Nigeria is about to build there. Though our leaders have chopped the money, shall
No, I've heard of it, but I've not passed there before.
they have passed the place. The site is still there. The banner is there. But there is not even a panel. One panel is not even there. They did not even clear the ground. You don't see the banner that we want to do this thing though. But we really have some rubbish leaders here, Sha. May the Lord help. Seriously, they are really dealing with us. I believe we should come to a level. There are people in this country. I've met people that they have something in their head to offer. But
yes, actually, yeah.
But
Did you hear the information about the boy? It's a mini hydro dam. Forgotten the school while we were still in UNN. The boy made a small hydroelectric power source. You understand?
yes,
Government applauded the person, and that was the end. We've not heard about the boy again, nothing.
And this is what the white men are really utilizing these things against us. They will come and carry
Okay.
that guy from Africa, take them to their country and drain him. I mean it, drain the guy, drain him of everything he has in his head. It shouldn't be now on a very good place. It shouldn't be.
Well, this is our country.
Well,
Hey,
maybe God can change something. Let's continue, sir. Maybe,
yes.
because when men decided that they don't want to, the sun and its radiant energy. All right, we are still continuing. So solar cells are devices which convert solar energy in form of radiation directly into electricity. Now I need to explain what the key word here is actually directly. The key
Okay.
word here is actually directly. There are so many energy systems that you will find around. There are so many energy systems you will find around. What they do is that they convert one form of energy to another. But what we are saying is that in solar, welcome Mr. Onadite. What we are saying is that in solar cells, what they do is that they convert it directly to electricity. Now, for instance, if you have a steam power plant, you want to generate electricity, what you first of all do is that you burn your fuel. That means you convert your energy stored, a chemical energy, into heat energy. From heat energy, you use it to boil water. From boiling water, you convert it to a mechanical energy, you use it to turn a turbine. From turning a turbine, you convert the turbine shaft to a generator, and you generate your electricity.
Mm-hmm.
But what we are saying in solar cells is that as it's taking the form of energy from the sun, it's giving you electricity state. It doesn't do
Wow.
any other internal conversion from one form to another form to another form to another form. So as you get it, you get electricity state. Now, there are so many systems that does that. So all energy system that does that, they are categorized under one topic called direct energy conversion. One of them is TEG, thermoelectric. It does the same thing. It takes one form of energy directly to electricity. One form of energy directly to electricity. That's what we mean by
All right.
direct energy. Fuel cells is another very good example of direct energy conversion. So solar cell is one part of them. So they use light sensitive cells to convert the photo energy into electric. They use PV system, photo meaning the light, then photic referring to electricity. So you are welcome, Mr. Onadi.
Yes, thank you.
Yes, sir. All right, sir.
Thank you, bro.
Yes, sir. We have been like 30 minutes into this class, but let's see how it happens, sir. But we are just laying the basis at which electricity is generated from the panel, and some ratings.
All right.
Those values you see, those ratings you see, where they come from and how they that's what we have talked about. Now,
All right.
I really want to, I don't know, maybe I should just, I believe many people here said, so I will just explain some things. Photovoltaic, I want to explain what is this effect. Now, you see what generates electricity from solar panels. There's a lot of noise from there, sir. Sorry. So, what generates electricity
I
from?
really can't.
I just moved it now. I've been able to control it. So,
Okay.
now let's continue. You see that thing that generates electricity from this guy is an effect. It's an effect. And that effect is what I want to explain. So, and this effect is not specific to solar panels only. That thing happens to all material. It happens to all material. Now, let's take an example. I have different materials with me here. I have a paper, I have a tape, I have a mouse, and I have a solar cell behind me. Now, if you leave any of these materials or any of this material outside, please, I need our answer. What did we think it will happen to them? Let's say I leave three of
They'll
them.
eat up.
They what, sir?
Eat up. Come
They will
on.
eat up. Yes, sir. You are correct. They will eat up. Now I want to explain the science behind the eating up of those material. That's what I want to explain. So that it's a general phenomenon. That heating up is what is generating energy in solar panel. And that's what I want to do. Then we begin to link things up from there. Now, you remember from secondary school chemistry, that average kinetic energy of a molecule is directly proportional to its temperature. That's one of the kinetic theory. Now, what we are saying, and the molecules of solid are closely packed. That means they have a small loose space for them to move. I will not do so much theory, but I want us to understand the basis. Now, look at what happens.
I remember.
Yes, look at what happens. Because the molecules were close together, what we are saying, if you understand that theory, the theory says that two things can be converted: the movement and the temperature changes. The movement and the temperature changes. So what we are saying is that if peradventure you see material being heated up, then what happens to that material is that its temperature has been, its kinetic molecules has moved. Hello?
Okay.
Please.
Hi.
It's convertibility. If you touch a material, like if you touch a material now and you feel it, you feel that the temperature rises. What happens internally to that material is that the molecules have moved. Average kinetic, average movement energy is directly proportional to temperature. Similarly, if the molecule move inside, what you observe outside is that the temperature will increase.
Okay.
Now, what happens is that by the time the photons enters into a surface, this is a solar cell. This thing was what was combined together to form this guy. So all the science I want to explain now is the science that happens within these solar cells. They actually, that's one of the things we'll be doing in this class. I'll be teaching us how to combine the solar cell, make a solar panel of our own. But I'm just trying to explain what happens within this guy. What happens is that as these photons hit the electron, it transfers. I don't know if you have actually observed this before. If you have observed this before, that in the night, if you on a torchlight, you will see some tiny particles that is running out of your. That thing is called photons. No, as they are now running, now they carry momentum. They are moving. They carry momentum energy. So by the time they hit the surface of your material, any material whatsoever, it tends to transfer that energy into the electron. Why? If you remember very well in basic chemistry, that Lord Rutherford says that atom is made of a nucleus and electron revolving around the orbit. So if you come and hit an atom, what is the electron? That is the reason why the electron is the one that is responsible in chemical reactions, because they were the one that directly interact with what happens outside. Now, by the time the photons hit this guy, the electrons jump out. Molecules shake. Now, I want to explain what happens inside conductors. Conduction is transferred by conduction to explain that. If you imagine that this guy is a metal, and you put a source of heat here, like a Bunsen burner or a lighter, the heat will be transferred from here to here to here to here to until when it reaches your hand. So at a certain time, your hand will start feeling the heat. What happens is that I want to demonstrate what happened on my table now. What happened on the table is that, imagine these are molecules now. These are molecules. So this guy moved, he moved this guy moved, he began to move this guy. See when the movement reaches your hand. Now, the same thing will happen if you drop all other objects outside. As the electron move, they keep on hitting each other. The molecule keeps moving, then you begin to feel the heat. Now, what happens? You will have discovered that adding being you put a metal object outside and you put an insulator object. A metallic object will get heated up faster than a non-metallic object. Reason being that in a metal, there are more valence electrons that are free to move. What is the definition for valence? How simple can I explain what a valence electron is? If you take an onion, you take onions in your hand. That last part of onion that you can just do your hand like this and the thing will peel off. That one is called the valence electrons. So there is this part of electron that you can easily remove. So as the
Yeah,
first one, that's the valence electrons. So now what happens is that because metal has more valence electron, so it can easily generate that movement very fast. And by generating that movement, you can get more heat. So because more movement will be generated in metals. Now, please, did we get this thing that I just explained now?
yes, I understand.
Yeah. Now, conversely, con- conversely, sorry, conversely, if you take the metal, that hot object from outside, and you take it inside, it return back and being cooled again. You know what just happened? What happened is that the loose electron revolve around, and find another place and get himself there back. This class is not actually a theoretical class, but I really like people getting the basis. Now, what happens there is that the free electrons find a space again, return back to its position, or return back to any other free position. Everybody rearrange themselves, then they come back to another positions. That's basically what happens. Now, what is the difference in solar cell when you put solar cell outside? You see that effect now. It doesn't specifically talk whether it is whether it's a solid, whether it's a liquid, whether it's a solar cell, whether it's not a solar cell. But what makes solar cell different? How did we generate energy from solar cell? Because I really need you to get this. You are the only one online now, sir.
No problem.
What we want to do is that as the free electrons comes out, we want to sweep it out as fast as possible. Now, how did you get electricity in your house? Electricity is gotten by something called potential difference. What is potential difference? What is potential? Potential is capacity. Ability, that's potential. When you have ability difference, then you have electricity in your house. Now, let me explain that. Sir, which course did you study? Civil. Okay,
Yes.
you should know a little bit about fluid mechanics. If I take a cup of water and I take my straw to suck, if I just put my mouth like this, you will not get any drink. Until when I create a lower pressure, a vacuum pressure from my inside. Now, what does that mean? If you will make fluid to move, there must be pressure difference. That is why we place our tank overhead and we place one tank down just for transfer of fluid. Now, if I take this paper like this, just imagine, the pen will not move until when I create a potential difference for the pen to move.
Okay.
What drives electricity is that difference in potential of two wires.
Okay.
If you plug a multimeter, we will be working with multimeter so much in this class, so much, into a light, into a socket. When there is light, you will measure 220 what? Volt. 220 in the difference in the level of this wire, so they are having 220 energy differences. Then if that happens, we can push electron. That is sufficient to cause electron to move. If you have that, electron will move in that. That's the science. Now, we want to use that electron that comes out, that potential that we receive, that energy that the photon carries that knock out electrons. We want that electron not to come back. We want to take it out fastly to the load so that we can get energy outside.
Okay.
That's the science. So what we are trying to generate is a movement of electrons. So to this very level, if you look at my screen now, to this very level now, where photovoltaic effect happens, electricity is not generated because there's nothing special in that effect. Seriously, because it happens to the solid, it happens to non-metal, it happens to an insulator, it happens, everything experience it. The only difference is that solar cell is designed to always have excess electrons on this surface.
Okay.
So it's a two particular substance that was sandwiched inside this thin layer. This layer is about I think 0.25 micrometer. So now, how did we do that? It's just a spray. It's not really something like that. It's just like you spray, you have a base material, you spray one particular material, you spray another material, a particular material on it, then you have the solar panel. It's as very simple as that. You have a metal contact. In short, the latest technology in solar panels is that scientists have been able to derive a two kind of paints that can function as a P materials and N materials. What's the advantage of that? The advantage of that is that you don't really need to have a solar panel again. You have a house, just paint your house with that two paints.
Okay, that's nice. That's nice. So
So
it's not remove the need for buying solar panels.
yes,
Fix your house.
yes, and the stresses of you cannot. There's a now if you spray all your roof now, you can easily do with that. But the technology is in US currently. I'm so certain of that. You can actually browse. Scientists have been able to come up with that thing, and it really makes life easy. So if I have a roof now, I'm in short, in my effort, I want to try and get those paints. I want to buy it, but for now it's still expensive. But the moment I be able to get money, I will just get them, because I felt that it removed the constraint of this guy, that you have to lay the panels, you have to do this, so you can really have any surface. People are in latest phone that will be coming out now. One of the things you will see is that, in short, you can browse about the technology. Circuit board are now being built to the surface of a substance. I can send you the video, sir, where circuit board. So naturally, if you remove the back cover of your phone now, it comes with the speaker. So the moment you put the back cover like this, some circuits that they need to design in the plate has been there already. So now some of the latest technology is that you will have they just paint your phone. The moment they paint your phone, the back cover of your phone with the N type, the P type material, then you will have a solar panel at the back, and that can charge your phone wherever you are, where there's light. So far there is sunlight. Now, let me share my screen again. I think share the screen. All right, sir. Now, so this effect. So we need two materials. One in excess of electron, one in deficit of electron. That is how it will work. If you imagine the explanation I make now, that electrons will be freely generated somewhere, because this one have excess electron now, there is no space again. So if you mistakenly lock out one electron, it doesn't have another space it can enter than to find wires that was connected on this surface. Go to that place, because it doesn't have, it's already excess electron. Now the other side here, this place is the positive connection, this place is the negative connections, to tell you that it's really two different material. So if you now, the other material now, this one is in need of electron, so the electron find easy means of crossing and returning back to this place. And what is our aim? Whenever we say we have potential difference, what we are just trying to do is to move electron. If electron can move, then we have electricity. Now, in the reverse way, what could have happened, sir? What could have happened that would have stopped this effect is that if electron can come from this place and go down, that will stop our effect.
Sorry, please. It's that's the. Please, can you just go over it one more time?
All right. So let me take the two now. Sorry, it breaks. It's very fragile stuff. So let's say this is the P material now. This is the N material. Then we added them together like this. So this one has excess electrons. Now what we are saying is that this process will have been spoiled if electrons can move from here back to this place. But there is no way, there is no path in that place except the electron have to go through this place.
All right. Okay.
Now, that is the concept of a PN junctions. Let me draw a PN junctions for you and explain how it works. It's like a gate. Thank you, God. It's like a gate in civil engineering, a gate for holding waters in a dam.
All right.
Now, so this is the P side. This is the N side. Okay, sorry, this is the P side. This is the N side. The only time this gate can open is when you are coming from the positive side and you open this guy. But if you want to enter from the N side, there's no way. Let me position it very well. So
from
yes, this is the only reasonable direction. If you are applying a force from this direction now, it will never open this door. So what the junction immediately do is that they create a junction like this where electrons cannot go back. That the only thing you can do is to follow any path that is available here and return back.
All right.
So this thing, this PN junction thing, is not a thing of solar panel. Let me be sincere with you.
Okay.
You will see that diode is PN. You will hear that transistor is NPN, PNP. These things are just what I just explained. So it's not an effect that is maybe solar cell. If you have two differently doped semiconductors and you put them together, you will form a PN junction. It's as simple as that. That's just the truth. So in a diode use a silicon gallium diode. But in this one, they use two different silicons, doped by different metal. That's why I want to explain later. I'll just introduce the concept of doping. How did they make one SS positive? How did they make one SS negative? In Nsukka, there's a place called Obimo. In Nsukka, there are presence of sand there, sand, heap of sand. Where in Nsukka, if you have ever been to where they are constructing, you will see white sand. They use white sand in Nsukka. They get those white sand from Obimo. The problem we have with already available silica in everywhere in Nigeria, everywhere, all this sand is that they are mixed with so much impurities. The original silicon is actually white. It's not actually. If you have ever seen pure sand around the beach, you discover that they're actually white. The one that water keeps on washing over the time. Now, so there's excess work of doing the washing first before say you want to extract the silicon, you want to remove oxygen atoms from it. But I always see Obimo as a potential for Nigeria for manufacturing of solar panels. That's just the truth. Because I know in the next 10 years, we cannot finish the sand in Obimo. It's as plenty as that. I'm telling you, the thing plenty. That's just the truth. I don't know why we don't have visionary leader that can just look into this thing. Let's start doing these things. Let's start doing this thing. People can actually do it if you give them chance. It's machine that the white man is using to produce this. Bring the machine here. We have the raw materials here. It is here they will buy the raw materials. We send it to them. They bring the finished products in an expensive way. The same thing that is happening to crude oil is happening to every sector. All right, sir. So now the concept of O's and okay. Let me do a little work here. A little. In basic chemistry, if I write Al3 plus in basic chemistry, what it simply means is that as an aluminum ions, what simply means is that aluminum just lost 3 electrons. So what happens is that aluminum ion is in excess of positive electrons. It's 3 plus. He lost 3 electrons. So what we are trying to say is that in real sense, he lost 3 electrons. It wasn't that he gained 3 electrons. He lost 3. Now, what happens is that he's in excess of positive. That if you touch aluminum that time, you feel that he has excess positive than negative. That's what actually happened. Now, that's what leads to. You now know that the moment an electron leaves the surface of a P junction or a material, what turns that material is that the material becomes positively charged. Why it doesn't shock you, why you don't feel the shock is because the electron is still within the metal. So whether it's present there or not is because the whole thing will still be electrically neutral. But he has moved from his place. So that his place that he left is what we call a hole. He creates a cavity. That cavity where the photons knock it out from is called a hole. Now, that makes a hole to be positively charged. And that's just the definition about how hole is a positive charge. I'm trying to move faster.
No problem.
Doping is adding impurities, and that's why I want to do a small work there. Boron is a semiconductor material that have only 3 valence electrons and on spin. Then if you add boron to intrinsic semiconductor, then each boron atoms will bond with 3 atoms of silicon, leaving 1 covalent bond of silicon half complete. If you do the math, if you do the chemistry, you will discover that if you actually add, silicon is a tetravalent, boron is a trivalent. So by the time you do that combination, you have excess electron. That what the electron is waiting for is something to push it. Then start moving. So when we say that we make it excess electrons, that's what we do. We combine it with another material that when they do their combinations, there will always be 1 electron outside or 2 electrons that can be easily moved as a valenced electron. That's the gist around it. Now, the problem along that line is that it's what we call solubility problem. I will just read that line to you.
All right.
The concentrations of boron is quite low. Usually around 1 atom of boron to each 106 atoms of silicon. All right, some people are joining. I'm trying to bring them.
Welcome. No problem.
Yeah. So what we are saying is that the concentration of boron is actually low. That means that for you to add boron directly to silicon is a lot of work.
Okay.
Now, later in the day, by the time you now look at that, atoms according to Avogadro's law, I think 10 raised to the power 23 for 1 mole. That's what Avogadro's law says. So we have a lot of atoms. So by the time you keep adding borons to it, sorry, you are welcome. We are trying to explain what happened in solar panels, how solar panels generate electricity. Mr. Justus and Mr. Ben. Mr. Ben has been with us before, but I think network. Now, so later in the day, the overall net charge of a semiconductor is still neutral. Because the boron tends to you can't add as much silicon to boron. Because solubility will not allow you to do that. If you really read a lot about alloying, how metal comes together and form this, you discover that there is much to it. One of the much to it is that what is the interspecial spaces between one atoms and the other atom? That's where the other atoms will fit in. So if that second atom is bigger than the first atom, you won't be able to form them as an alloy. You have to do some other technology to make it work out. Now, so by the time they add borons to silicon, they form a p-type. And all these things I'm telling you, what happens is that when you first of all get a silica, a sand, you tend to wash it, you remove all the impurities from it. After you remove all the impurities from it, you try to heat it up. Any process of removing the oxygen, the O2 there, you remove the oxygen, then you form white silicon. If you ever browse how silicon look like, it's a white material. Then when you form the white material, they tend to convert it to something paint-like. But the process is actually extremely dangerous for human health. So now they spray the silicon upon a surface. They put a metal contact there. They spray another silicon, the another doped one on the other one, and they form it. So how did we get the N-type? The N-type is getting by phosphorus. Anytime you had 5 pentavalent impurities to silicon, sorry, Mr. Ben, we have done a lot of things. Sorry, I know you were out for some time. So what you form is an N-type. That one is in deficiency of electron. But the problem is that the electron from the p-type cannot just come to the N-type because of that gate effect that I explained of p-n junctions that I explained before. All right. Also, the concentrations of phosphorus atom is again quite low, typically greater than that of boron, because boron needs 1 to 106. It needs 1 to 103 atoms. So that's how they form the N-type. I'm trying to. I will still give us the opportunity to ask questions. So the moment you add these two materials together, the p-type and a material that is in excess of a semiconductor that is in the excess of positive charges and the one that is in deficient. You know, the negative now, it's not really means the absence of electron. It means that is in deficient. We have made the electron more than, that's what the magic is. If you add those semiconductors together, what you will form is a PN junction. And I explained to us that PN junctions is by no means a solar panel thing. It's a real life effect. Now, let me do some little work for us so that we understand. Please, I don't know if when you are not around, I try to explain what a PN junction is. So I really just want to do small work again. So this is how a PN junction looks like. So why this side is a P, this side is a P. So this place is a different material on its own. Everything here is a different material on its own. An N dope type, a P dope type materials. You combine them together, they form something like a gate naturally. Now, you see, for a PN junctions, please, are we together? For a PN junction, they have something. This is core electronics. I did a lot of things in electronics. I have a lot of knowledge in electronics. Now, if you have a PN junctions, the amount of potential you required, if you just look at your door now, your current door now, the door of your house now is a very good example of a PN junction. You discover that if you are coming from outside, you can easily push the door and enter. You can easily push the door and enter. But if you are coming from, if you want to go outside, you have to pull the door. Sure, we understand. Yes. Now, you see that the amount of energy you need to enter and the one you need to go out is two different things. But if you have a very big man that can break the door, you can still break it in that same direction. Now, what happens in PN junction is that the forward, we call that in forward bias voltage. That is the voltage potential difference you need to follow this line. Sorry, to follow this part. That thing is called the forward bias voltage. The one that you need to move from the positive to negative. It's easy, it's small. You see, for every semiconductor, that value ranges between 0.43 to 0.67 voltage. For all semiconductors, anyone you combine together. So what we are saying, you will see why this is very important. And I will show you now why it's very important now. Why what I just said now is very important. You don't need to tell me the voltage of your solar panel. The moment you tell me your solar panel, I can tell you everything on it. It's now. Now, this is an 100 watts behind me. Because it has 36 cells. If I count it now, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 in a row, and 12 in a column, 12 rows, 3 columns, making 36 cells. Now, if a PN junction is 0.5 voltage, and this thing is connected in series, voltage in series is addition of all the voltages, then I expected this panel to be 18 volts. That's the truth. Okay. It's as very simple as that, because that is it. So if I turn the back of the panel now and I show you, this color is 18 volts. Because that is what the theory says. Because it's a combination. So if you want to build 30 volt system, because one of the things we'll be doing in this class is that, tell me any panel you want to build in this world, I will tell you how to go about it. I'll tell you the combination of what you do. You know, there might be things you want to do. If you still need 100 watts, yes, sir. Are you with me? If you need 100 watts, that is at 200 volts. I'll still design it for you. You know, this is 100 watt panel and it's at 18 volts. If you still need 100 watts at 200 volts, it's still possible. So that will be the basis of our next class when we actually look at how to calculate.
How you to tell it's 100 watts? You need to describe for the 18 for the volts, but for the watts, how do you know it's 100?
All right.
That's it.
Each cell has 2.85 watts or 2.65 watts each cell. That's the energy generated by each cell. So if you do 36 times 2.85, you will get 100 watts. It's as simple as that. So I really know the nitty-gritty. I follow the data book I read data book for solar cells. So I really know what they can do. I know what their ratings is. This one, the solar cells used in this place, it's not that Nigeria is a very bad country. It's not the effective one. The highest effective one is 6 watts per cell. This one is the very low quality one. It's around 2.85 watts. They won't send such panels to Nigeria. I tell you the truth. It's only used outside the country. So what we are saying is that as big as this 100-watt panel is, if they have used the 6 watts per cell, it will just be half like this, and it will generate 100 watts. Because they only need to add 18 instead of 36. And they will still get the result. So what we are trying to say is that, so because each one is a PN junction, and PN junction has a standard voltage. Now, what I was trying to explain is that you can also come from this way and enter to this door. But if you are doing that, remember that you have to break this door. Your effort will be to break this door. If you want to come out from your house now without hindrance also, is that you have to break your door and force your way out. That is what we call a reverse breakdown voltage in electric. This thing is not a solar thing. That's just the truth. It's purely electronic thing. It's a reverse breakdown voltage, and it's always high. Now, what we are saying is that for electron to tend to move from the other side, they will have to have a very big potentials, which is not going to be possible. This is the concept behind your power supply. The power supply for your laptop, your phone charger now, that is what is happening behind it. Another day, maybe anytime God give us chance, we might look at electronics class. Now, this is what really happens in the PN junction. So now, I come again to our previous explanation, where this guy is in P type, this guy is the N type. This guy has excess electrons. But from the design, the electrons cannot move from here to here because of the gates in between them. So as you knock out these electrons, I've explained what happens, how the energy comes, how they knock it out before. As you knock out the electrons, it doesn't find another means to find a means, which is a root, which is a wire you have connected here. That's the only place, because there's no other space you want to combine again in the P type, because we have already loaded it with excess electrons. So you find this way out to this place, to your load, to anything you design, then it comes back and returns back to the N type that's already missing. So the only direction electron can flow is just to flow from the negative one, from the positive one under to the negative one on the top. So I explain again. So you have the positive one under, you have the negative one on the top. So as you push electron from here, you push it to this place, it goes through the cycle and it returns back to this place. And that is the basis for a solar panel. Now, if you combine several panels together, you form a solar panel. So in our next class, sorry, this is what happens in PN junctions. That's what you are seeing on my screen. Depletion regions. I will only explain this particular. Now, next class, I'll be teaching us how to actually size any panels, design any panels, where to get the solar cells from. I will physically here solder all these things. If there's light, I will solder it together. You'll see how it is being soldered. I will solder it together and I will show you how they soldered it, how they connect it. Then how to know what will be the length of this place to this place, the height of this place to this place, the calculations behind it. I will teach everything that involves that. Now, all right. Okay. So now, if we look at my screen currently now, you will see what I just explained, a summary of everything I explained now. That what happens. This is the top negative contact. This is the bottom positive contact. This guy is here. Then this guy is here. Back contact is here. That's the back contact. Admin, I have meter very close now. Even with the intensity of the sun, I will have measured it for you. You have seen that there's power generated even with this currently now. Now, what happens is that as the sun hits the electrons up here, they find their way out, because everywhere here has been occupied. You see that even as he is an N material, as he hits this place up, he enter inside, he wanders and wanders and wanders and wanders. There's no space for you to combine it, because naturally electrons are also flowing in this direction. So it goes through the load. So the load now, everything, your inverter, your battery, everything is connected in between these two lines in real life. So it goes through it, follow through the load resistance and return back to you. All right, let me just show us some things. So the whole theory I've been trying to explain is summarized in this view line. Electrons with higher energy level flows out of the cells through the wire to the load. After releasing the excess energy into the load, these electrons return back to the cells and fall into hole. As soon as the electron leaves the cells from the other side, it enters the wires, and this process and this cycle continues from step 1 to step 2. Let me ask us, is there anybody with questions now? Before we just look into some few things that we have for today. Any question? Oh, there's no question. So I can continue, Shay?
Yeah, go on.
All right. So if you take a solar panel, what will you see? So if you cut it like this, what you will see is that you will see the aluminum frame, which is this guy, this frame. You will see the glass cover, which is this guy. You will see the ethylene funcine acetate. It's a material. I have it also inside the house. I will show you in the next class. Just remind me that I said I want to show you ethylene funcine acetate. So
you call it azelene fitting
acetate. Sorry, I'm not a chemistry person. So it's been, though I'm an exceptional student in chemistry. I love chemistry so much. You will have seen it in my explanation of that I fell enough. So another anti-reflecting coating, ARC, is the layer you will meet next if you cut this. Why? There's a concept called the Holocaust. Not Holocaust, Holocaust cost in heat transfer, heat and mass transfer. Now, the concept is that if you form a spherical object and you mistakenly allow rays to enter that thing, we want that rays to lose all its energy inside that spherical thing. What happens? If the ray enter here, it hits a particular wall, when you turn by it keeps eating inside, and it was trapped inside. Now, the problem is that if you know that at the beginning of this class, I explained that 3 things happens to radiations. It can be reflected, it can be absorbed, and it can be filtered. Now, as the sun radiations hit the surface of this guy, you want to escape also, you want to be reflected also. So engineers was trying to do all their best to make sure that the radiation did not go out. So he hits something on the top, he returns back into the cells. So that's what the main function of that layer, just to prevent radiations from being reflection. You will see the reason why as we go along. You will see the reason why the N materials have explained, the P materials, which is this guy itself. The N and the P materials is in this guy. The metal contact, the ethylene funcine acetate. If I turn back now, if I turn this panel back, you will see it's a white material and the Teflon PFD layer. If I turn the material, the panel back, you will see all these materials at the back. Okay, I don't know. The space here is a constraint. There's this material inside this thing. I don't know, maybe you can see it. It's white. It's inside it, but I will show you. This is the Teflon. But there's a material here. It's like a nylon. That ethylene funcine acetate is like a nylon. It's here. Very close. But don't worry, one of our this class, I will bring the raw type that they have not used to make panel at all. I will bring it for you so that you can just see it along the class. All right. So if you everything I explain about what they do, you will find it in this slide. That's what this slide is talking about. Then I need to explain this. This is one of the interesting parts. Very interesting. Irreversibility in solar cells. And when time we talked about irreversibility, we talked about what makes solar cell not to work well. At this very junction, I need to tell you that don't be deceived. Solar cells are not the best energy conversion system in the world. They are not. They are not, and they cannot for now. They have a lot of losses. In short, they are not effective. So just follow me as I do the math. Let's do the math together. So if you measure this place to this place, it's 540 mm. If you measure this place to this place, this is about 150 mm. If you do that calculations, that will give you around 1 meter, 1 meter square. So this guy is about 1 meter square. Mr. Ben, you are with us at the beginning of this class. We said solar constant is 1000 watt per meter square. Sure? What does that mean? That this guy should give us 1000 watts. If we know simple mathematics, is it not true? But conversely, is giving us 100 watts. That shows that is 10% efficiency.
We need 10 of it.
Sir, let me hear you, sir.
Is it that we will now need 10 of that?
And more space will be occupied. So it just shows that the guy is not really efficient. You need to know that. Even if somebody outside, it takes an engineer to know. Somebody, it's working. That is what everybody is trying to understand. But they don't understand the fact that solar system is not actually the efficient one. So what we are saying is that there are a lot of issues inside it that give it irreversibilities. Reversibilities are what are the reasons why it's not 100% efficient? It's not 100% efficient. And there is no, of course, you know that cycle efficiency and thermal efficiency for any system is never 100%. Now, so one of the errors we are having is that we are having reflection from the surface of the cell. We are having light energy too energetic enough to separate the electrons from the atoms bond. That means not all the energies that comes to the surface of the cells have sufficient energy to actually cause these electrons to leave their place. Some were too energetic, some were less energetic, and they are resistant to flow of electric currents. Self-shading. If you see now that they will be self-shading themselves, because you need to put wire here. Certain area of the cells is covered already. So that's the reason why that's one of the reasons why we even have small wires that are doing the job. Don't worry, you will see the wires. I even have the wires here that they used to connect it. I will do the connections for you one in the next class. So performance degradations not at optimal temperature. If you have observed, if I have turned the back and you see the optimal temperature of this guy is 25 degrees Celsius. I did a PhD work with one engineer some time ago, and his PhD work is about how to improve a solar panel efficiency by trying to cool the panel. We are trying to maintain 100%, 25 degrees Celsius behind. Now, while we do that, I don't know, maybe you can just picture it. We have two cells. One panel, we are cooling it. The other one, we are not cooling it. So we are trying to measure the performance of this guy. Both of them same rating, same manufacturer. But for this guy, we are trying to cool it from behind. Now, we are measuring the amount of heat that was entering that air that we are using to cool it, so that we can use that heat to do that hot air now to do another job. So we are trying to gain from the two ways. Did we get hot air, and is our panel performing more better than before? That's what the PhD project is all about. Now, so definitely there are things we can do to keep improving it. People are really working. Causalities of such systems. It doesn't have a moving part. Made from special semiconductors. It's a solid state device. That means there's no fluid at all. There's no fluid at any time at all. There's moving. No pollution, no exhaust. Rapid response. This is the awesome part of, one of the awesome part of the solar panel, is that if you have to start a power plant, if you want to start a power plant, you must have started the power plant 6 hours before the power plant will start generating electricity. That's it. Because it takes time for the whole water in the system to get to the boiling temperature. And you know that they boil water at high pressures. So the boiling point also rises in accordance with it. To generate the steam starts turning turbines. So it takes a long hours before that happens. But in solar cell, the moment light falls on it, plants to get electricity. So its response is like first order, almost first order. First order is y equals to mx. That means whatsoever your input is, you get an output. At least you get an output. But in other power generating system, it's not like that. Little maintenance. All you have to do is maybe to clean the surface, and that's all. High power to weight ratio. Yes. If you carry another 100 watt system, in combined with you are checking their weight to solar panel. Solar panel is definitely going to be more lighter than it. But in conversely, low power to area. It occupies a lot of area. Just imagine 100 watts occupying this big area. Then what is, so if you have a 4.8 5 kVA generator that is just occupying that small space, if you have to have 5 kVA of this, you have 50 of this. So every place is just occupied. That's the messy part of solar panel. Then solar cells was combined together to form something called solar module. When solar modules were being combined, they form something called solar panels. When panels are combined together, you form something called solar arrays. When you combine some solar arrays together, you form something called solar farms. All right, that was the explanations there. Everything here, I won't deal with it today. We'll be dealing with it on the day we'll be looking at. But, question?
These slides will get deeper.
Sir? This slide.
The slide, she will get it. Yeah.
The slide. All right.
The PowerPoint presentation, the slides.
Let's see what we can do. We'll see what we can do about it. I'll discuss with my friend here on his permissions or on the permission of the circuit.
Thank you.
I will release it as. All right. Applications of solar PV systems. Where can we apply them? We can apply them in utility interactive systems. What did we mean by utility interactive systems? This is when you actually have a light in your house. Utility, you have a light in your house, a NEPA supply, and you have a solar panel. So they are interactions. When they took the light, the guy comes in. When the light comes by, the guy pushes back and the whole thing. So they are interacting. A standalone system. A standalone system is the one that you don't really need electricity. Everything that's supplying your house is pure solar. It's possible. And residential applications to power lights and household appliances, agricultural applications for irrigations, industrial applications, telecommunications. There are some mass now that they have been powering them using solar panel. Public services applications, health ed applications. Some people use solar panels to generate electricity in a very good country. If you generate electricity from your solar panel, you can actually connect it to the national grid and the government will be paying you for giving them energy. But don't try it in Nigeria. So why PV system? Is because the cost is low. This is somehow. It's only low in remote location. It's only low over the years. The problem of solar is that it has high initial cost. And I felt that if I have time, I could explain more about this. I don't know if anybody has heard about something called programmable logic controllers before PLC. PLC is used in manufacturing industry. PLC should not be expensive, but it's expensive. PLC is not even in capacity as strong as your laptop, but it's expensive. Because they don't really want it to be available for local people. The same thing is happening in EV. Solar technology is fighting war against oil. You know, war power is in oil. So they really don't want it to be cheap. They know that if it's cheap, if everybody starts having solar, you have solar car, you have electric car, and it's a renewable, then fuel will go down. So they make the initial cost too high for everybody to be able to afford it. So the problem with solar system is actually high initial cost, which pays off over the year. So if you use 250K now to get it done in your house, by the time you use it for this solar panel has 25 years warranty, as in you can serve it for 25 years straight up. So by the time you spread
So that means
it doesn't.
The panel would not die within 25 years. It takes longer than 25 years for the electrons or the
it will not die. In short, after that 25 bar, it's nothing that it will spoil. Its performance can just be degraded. Like it can come down a little bit, it will decrease. So, but now if you spend 250K over 25 years or over 5 years before you change your battery or change anything, you discover that it pays off. But it has high initial cost. 250,000, I don't have it. And that's the mechanism to push people away from the whole system. All right. It's like Zoom are telling me that they are giving me less than 1 minute, but let me quickly see modularity. So you can add the system up. You know, if you buy a new generator to the generator in your house, you can't add the previous gen to the new gen. For example, you just buy a new fridge. Your house is 6 kVA before. Now it's not 10 kVA. You have to go and buy a 10 kVA generator. You can't go and buy 4 kVA generator and add it to the 6 kVA generator you have before. It doesn't work that way because impedance will not match. So now, but in solar system, it's not like that. You can add them together. It's modularity. You can combine the system. It's eco-friendly. So those are the things we look at and we say these are the advantages. These are the reasons why people rush into solar PV system. If I have done this, I've done a justice to this class. In our next class, we'll be looking at. All right, good morning to us, everybody.
morning.
Mr. Donald, good morning, sir. Mr. Silas.
Good morning.
All right.
Good morning.
So the last time we had this class, we were able to talk about fundamentals of solar PV technology, where we actually explain the whole principle, the whole thing that happens inside the PV system, how the whole energy generations happens and the rights. So we're able to cover the characteristics to the YPV system. Sorry, please, we are having visitors and we are trying to, that's what caused a little. Sorry, So, we said our focus today will be on the solar panel itself. And we're looking at how can I build a solar panel by my own? What are those things that I need to do? What are the principles I need to follow in trying to get one for myself? All right. Good morning. Yes, sir. Well done, sir. Yes. Yes, sir. Well done, sir. Well done. Yeah. Wow, sorry, I'm having desired attention here. Sorry. All right, can we start? Yeah. I think I'm a little bit balanced now. Can we start now? Hello.
Hello.
Yes, please let's start. We had the visitors
Okay.
before and the thing was, I'm having divided attention, but at least this is okay now. Let's start. All right. I think, can we see my screen now? Can we see my screen? Yeah. So the last time I was able to prove it to us that when you combine solar cells together, you form something called a solar module, like something you are seeing currently. When you combine module together, you form something called a panel. When you combine panel together, you form something called Thank you very much. Yes, sir. Sorry. Mr. Donald, how are you, sir?
I doing well.
Yes, sir. The sound is still okay. I can hear you now. Sorry, don't mind. There are many things that is happening behind the scenes.
I understand.
Yeah. Yes, sir. Bye-bye, sir. Yes, sir. So, we said that the last time we said that I will be looking at how we can combine a solar cell together to make a solar panel, and how can I solder them? What's the mechanism? What did I need to know about soldering them and all those things? I said those are the mysteries I will be unraveling today. All right. So solar cells are connected together to form a solar module. Now I want to quickly show you. So we will quickly derive a formula together this morning. So our focus this morning is to actually produce a solar panel from a solar cells. So, and in the last class, I was able to show us the solar cells. It comes in a pack like this, and so this is a solar cell. This is how it looks like. There is
All right.
combinations of it, what forms what you can see here. Now, so our work today is how can I solder them? How can I form one out of the whole thing? So, all right, let's start. So we want
Okay,
to
so
dive
you want to
yes, sir.
sorry, you want to make what is behind you that complete solar panel
Yeah,
from the solar.
cell. Yes, it's possible.
Okay, that's what we're doing.
That's what we are doing today.
All right.
All right. So we'll first of all start from something I called the electrical considerations. Sorry, I might have to be using my hand to type a lot. The last time I was preparing this slide, those things were not there. We are improving every day. So I might be doing some manual calculations so that we'll get it right. It's not. So we'll first of all do the electrical consideration. Let me create some new slides. So you don't mind me. So I'll call this electrical considerations. What are the electrical considerations I need to look into? Number one, I need to know the power I want to design for. Number two, I need to know the voltage I'm working with. Now, all right. So number three, possibly if I need the current. So if I need the current, how will I go about it? Now for the electrical configurations, the first thing is the power. Now, if you want to buy a cell from online, what they will tell you is that they will tell you the power ratings of each cell. You want to order a cell, so they will tell you the power ratings for each cell. And I told you that the power ratings for each cell. So for power considerations now, you first of all get power per cell. So I have all these things written down. Power per cell, which is equal to, for a given cell now, we have about 2.85 watts. Now, can I ask Mr. Silas, for our example this morning, so how many watts should we design? Or Mr. How many watts? Just give me the watts. There's something I'll show us later in the day.
Let's use 3.
3 watts. 3 watts is too small.
3.0. Yes, sir.
Let's go.
Okay. Let's see. 12.
300 watts. Let's do something like 300
Wait.
watts.
Okay. 200.
The panel behind
Okay.
is 100 watts. So let's go for something around 300 watts.
100.
100. Yes, this is 100 watt solar panel already built.
Okay.
So let's go for something around 100. So the power we are designing, or something, let me call it design power equal to 100 watts. So that we will see whether our calculation tallies. Let me just use 100. All right. Now, you discover that. Please, I want us to have this at the back of our mind.
Sorry, we are designing for 100 watts or 300 watts.
100 watts. We just want to confirm whether all our answers will be similar to everything here. So let's do 100 watts. In our assignment in this class, that I will request us to submit is that we will design 300 watts. Don't worry, you will do everything.
What about we multiply the answer for 100 watts times?
What?
By 3.
Oh.
You sabi math.
300 watts.
Now 300 watts now.
Hey, Sadena, you're not finished. All right. So, now, one of the fundamental things we need to recognize is that power is a conserved quantity. Power and energy is a conserved quantity. Now, what we mean by that is that irrespective of the way you combine your voltage and your current, your power will still remain the same. Please, just look at my screen. Let's do some math. Power equal voltage multiplied by the current. We all know this from basic physics. It means that if I say power, I'm designing for 100 watts. Abi? So if I take my voltage, no, let me change that camera. I just want to change my camera to the one that is the webcam, so that my friend
All right.
so I will share the screen, but my friend won't be stressing his hand. All right, let's go back our screen.
Don't go back.
Yeah, sorry. So that he won't be stressing himself. Now, okay, power equals to. So we are saying that anything you do to make your voltage of that system 25, that means your answer will be what? Your power will be, your current will be what? 4.
Mm-hmm. Yes.
Anything you do that make this to be 25, then if we go and check the corresponding voltage, it has become 4. Yeah, that's what it is. It means that anyhow you combine them, you can increase voltage, you can increase current. There are several circuits that increase current. There are several circuits that increase voltage. For anyone you are doing, something is going down for the other. Power is a conserved quantity. Now let me explain in terms of cash, in terms of money. So this is a 1,000 naira note in my hand.
All right.
So what we are saying is that it's either you have 2 500 naira or you have 1,000. So imagine this is 1,000 watts and this is 1,000 volts. So you have 1 current. If you go and cut it into 2 and you make 2 500 naira, it doesn't change the total answer. It's still 2 500 naira, 2 voltage, 5 current, 500 current. If you go and make it 100 naira times 10, it's still the same 1,000 naira, but you are changing the combinations. So you can change the combination. So for this particular thing, I can determine what my voltage is, but that wouldn't change the power. That's exactly what we are talking about here in this morning. Now, so before we look into that, we first of all look at, so we are designing for 100, so our design power is 100. Sure? Then the next thing you will consider is how many number of cells that I will need. How many cells will I need? Then that will be, because power is a conserved quantity, design power, that will be design power. Design power, everything divided by power per cell. I hope we understand. So,
Yes, sir.
this would be 100 divided by 2.85. 35.087. So we get this equal to 35.087. Now, this is more better than cells. Our unit now is what? So it's more better that we say that we are going to use 36 cells. 36 cells, please. I'm switching to another camera now. Just to show us that this panel in front of me now has 36 cells. So,
All right.
You are for it. So I want to count the cells for us so that we see that it's 36 cells. That's it. Are you on? So select camera. I want to change the camera. Sorry. All right. We are on. So this is 1, 2, 3. Can we see it? It's 3 rows.
No.
3 per row.
Yeah, no.
Abi? That's 1, 2, 3. 1,
Yeah.
Yes.
3. So let's count the numbers of the ones in column.
2, 3.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 3, that makes 36. And that's how they come about. They are going to use 36 cells for this particular one. So I'm switching back to my webcam. All right. So that's how they get the 36 cells. There's nothing like, so if you are doubting this, I can go online now. So if I go online now, I will show you where they are selling cells. We'll look at the properties of the cells. I think it's necessary from online. So let me share that screen with you now. That screen where I'm online, where we are looking at it together. Share screen. Google Chrome. All right. Share. I hope we can see my screen now. So I'm browsing now. So I will go to AliExpress. Sorry, we are still going to China.
We are going to China. Please put on your nose mask, so Corona now.
We are going to post this video online. Okay.
Sorry, China.
All right. So I'm trying to search for. So you are going for solar cells. Mr. Silas, are you with us, sir?
I am with you, sir.
Yes, sir. Hope you are following. So
Yes, sir.
don't mind us. We are like friends, like we know each other. So this is a solar cell.
No problem, sir. No.
So let's just look at it. So this one is 100 watts complete. We have all these tools. We'll be using all these to be making the solar cells. Like, let me show you some. This one. They are called tapping wires. Can you see them? You see the wire here? There's a wire here.
Wait,
I'll show you.
I didn't see the wire.
Don't worry, I will show you people. We are still going there. There are two types of tapping wires, which we will get there. Why are we having two types? So those are the wires you are seeing on my screen. You can see my screen now. You can
Yes,
see.
I can.
And that thing is called flux pen. I will show you also. We have all those things they just took our life now. Don't mind that. Now let's start from here. Geometrical consideration. We're still going to do geometrical consideration, so that by that time I'm quoting value, you will not argue with me. This is 124.4 mm. Everything is measured in mm. Against is a square of 124.4 and 124.4. So what we are saying is that if I measure from here to is 125. From here to here is 125. You need that to know your length and your breadth when we are doing geometrical consideration. So let's move on. So there are different types of cells. You can see them. TDB 125, TDB 125, 2DB 125. So you see their efficiency. You know, we calculate this efficiency the other time, and I was telling you that solar cells were not actually that efficient. So they are efficient. If you can just, Mr. Sayers, you can watch our first class, you will see where I do the efficiency calculations.
Okay, sir. No problem.
So the maximum power now is 2.7 watts. And the voltage, I told you that the voltage per set, the other class is 0.517. I told you because the PN junction, his voltage should be in that range. That is, then this is the current at maximum power. This is short-circuiting current. That means short-circuiting current is that when you bring the positive and the negative together, what are the currents you are going to observe? Don't worry, all those things I will try and explain to everyone. VOC is voltage of the open circuit. IMP is current at the maximum power. Then don't worry, by the time we are doing IV characteristics of a solar panel, we'll see all those things. But what I just want to show us is that the power per one, are you seeing where my cursor is? The power per one is 2.7 So if we go back to our calculation, I will share this other screen now. So I will share the other screen now. Share screen. So if we go back, we actually put 2.7 here. So our answer should be 37. 37. But there's a problem with dealing with odd numbers. So now I want to show us one more thing. Can we go back online? Let me show us one more thing online. That I just want to show us that there are efficient cells that are, this one is 2.7 watts per cell. So I want to show us that there are cells that are more efficient than this one. So I will browse 5 watt solar cells. Sorry, 5 watts. So this kind of cells, they were 5 watts. So please, can we just look up? Please, I don't know if you can look at this place. You see 10, 5 watts. Can we see it? The dimension was given 10 pieces. Where my cursor is now, 10 pieces, 5 watts. The dimension was given a high grade. That's what they give them. That means if you have 10 pieces and you have 5 watts each, that is just a 50 watt solar panel. That's what you are setting out to do. Did we get it?
Okay.
No.
Yes, sir.
If this why people now buy this kind of thing, they want to use it for us, they will not divide it into 2. What is actually they divide it into 2. But I will still show us to still come back to 2.7 by the time they divide it. So it's possible to get a more better solar cell. This is its electrical properties, and this is its power. You can see its power is that it's around 4. Yeah, it's around 4.94, 4.9 something. That's the power for this cell. So you can get more efficient cells. What more efficient cells means that you will be doing more in a lesser area. I don't know, maybe we understand. In a lesser area. So the area this one is going to occupy, that this one is generating 2.8 watt, 2.7 watt, is the same area that one of 5 watt was to generate. If you look at this, I've seen the kind of cell they use here. They use a 5 watt cell. Don't worry, we'll still make it clearer as we go on. But what they do is that they will not divide it into 2. All right. Okay.
We will be that. Sorry, you are saving online.
All right. Can we continue? So I just want to show us that is basically what happens. Now let's go back to our. You can't hear me. Hello, can you hear me? Mr. Donald, can you hear me, sir? Can you hear me? Let me see chat.
Yeah, the network is bad.
But can you hear me now?
Okay, I can hear you now.
All right. Can we continue? Did you hear?
Yeah, I'm hearing you.
Every explanation that I give about the numbers of cells, about the power ratings per cell, did you get all the explanations, sir?
You got the explanation.
Hello, sir. Hello, sir. Can we proceed?
Yes, we can continue.
All right. So let's move on to the next thing. So let me share my screen again so that we'll go back to the slide. What I just tried to show is that power per cell is given as you are buying, as you are ordering those cells. The power per cell, you can get them out. All right. Wow. Sorry. All right.
Did I just see classwork?
Sir?
Did I just see classwork?
Yes, there's classwork. There's class word. Now, all right, let's go on. So, what will my voltage be? That's the next question. What will my voltage be? Voltage. Now the voltage is about you. Just calm down. The voltage is about you. We know from elementary physics that if you connect cells in parallel, what's the answer? For cells in parallel, for cells in parallel, Abi? The answer is 1 over V, Abi? 1 over V total, Abi, is equal to V total now, is equal to 1 over V1, Abi? V1.
1 over V2, yeah.
Yes.
We know that. And you know that if you do that labor now, the total voltage will be less than the voltage of individual one. Don't worry, when you can solve that mass.
Yes.
Now, let me show us that these cells were connected in series. I just want to show us. So I'm switching my camera now. I want to show us that they are connected in series. I will show you the connection. You will see it, that it was connected in series. Let me quickly switch the camera to I want to switch my camera to another camera so I can easily show us. It's just sorry for the delay. All right. So I think we are on now. Let me show us that it's in series. Can you hear? Yeah. Sorry. All right. You can see the very first cell. I'm coming. This connection here is the central positive. This connection you are seeing is the central positive. Now, central positive goes down. Look at here. Look at this. I just show us what happened. Now, the mystery is that please come. Don't worry, I will still do all these things that we will see. Look at what you do. Just point touch to me. Point the camera. This is a cell. You take this is a cell now. You take wire, you connect. This is the positive. Now take it underneath. Now connect it to the negative. This way.
Negative.
You cut here. You will cut this place off. You do positive here again. You do another positive on top this one again. You take the next cell. You connect it to the negative behind. They were not continuous. Did you get the gist? I will show some pictures if I can send some pictures now.
Are you hearing me?
Yes? Yeah. Let me
Yes, that means positive from A, from panel A, from solar cell A.
Yes. Goes to
negative of cell B.
Yes. And you now cut it at the negative of cell B. Then you now join the negative of C.
Okay.
I will show us when our students are performing these things in class, so that you will see it in more clearer version. So let me show us from the panel again. You see the positive. Look the positive now. As it goes down, they take it under. It's not continuous. It doesn't come to this edge. Observe this place. They take it underneath. They join it at the under. They take another one on the top. They join it to the under net of the next one. They do the same thing down to the last one. And they continue. Let me show us that it's in series. When you get to the last one, just let me show them. When you get to the last one, you cross like this. You start the whole journey again up. When you get to the last one of this, you cross to this place. You start the whole journey.
Can you move the camera back? I can't really see it well. Thank you.
Can you see now?
Yes, I can see it now.
So when you get to this place now, you do another crossing. You start the whole series connections downward. So this place now becomes your central out. Have you seen your central output? And this start from it. Don't worry, I will still show us this again. Let me show us where our students are doing practically in class. Maybe it become more clear that way. Where did you copy? So I'm coming. UN. Sorry, please just give me some minutes. I'm coming. All right, let me share another screen with us now. Share screen, picture. Yeah, we are there now. You see how it showed that the positive. This is the soda positive. I just want to show us when they combine it.
What was I doing in UNN?
They carry block.
So you see them, they have soda them 1-1. They want to combine it now.
Okay.
It has combined this one now. You see?
Yes.
You see the whole row. It joined positive to negative of this one, join positive to negative of this one. Sorry, this is another class entirely. So
that Christmas light.
Yes, we train them how to code Arduino, using Arduino to code Christmas light. That's what the video is about.
You're eating your party.
So this is how you join the whole set together. You now determine the numbers of sets you want to join. So that's basically, so what is here inside this set is the series connection. That's what I'm trying to show us. So if I do series connections of 0.517 times 36, please can you just do the calculation? Mr. Silas, are you with us? Mr. Silas, are you following the class?
Yes, sir.
517
Yes, sir.
times 36. 18.61.
5.5.
Yes, that's 18.61. So I'm turning the solar panel backward. I want to show you the voltage, the output voltage, whether it's 18 volts. You see, this is maximum.
It's less.
The output. Can you see? Can you see?
Yeah.
Have you seen it's 18 volts?
Yeah, I can see it.
So that's exactly the way to get the voltage. So let's go to the current. How will I know the current that will generate if I do that? I can send us this. I think we snap that. So all solar cells has its own. Let me quickly go to one screen and share another screen with us. Stop sharing. Share new screen. Slide back. Share. All right. So let me go to this. This is I think this is 100 cells. So these are the parameters you see. This is a standard parameter for a 100 cell, 100 watts. So 100 watts now you can see that you have the voltage to be 18 volts. For a standard one, it's 18 volts because it must be 36 cells, and if it's 36 cells, it's 0.5 volts because it is a PN junction, which I explained in the first class. And you combine 36 of 0.5 is half now. That will be 18 volts. Now, I will do a little bit of a syllabus here. If you take a 300 watts, then what the voltage is supposed to be? I will explain some things that we never think that it is true, and those are the things I will be explaining in this class.